Welcome to this next video in our discussion of kinetics. In a previous video, linked in the description below, it was shown that the order of any reactant is determined by the number of times it appears at or before the rate determining step. This was shown by showing two reactions, NO2 plus CO going to NO plus CO2, 2NO plus 2H2 going to 2 waters and nitrogen. By kinetics, the first reaction would have an order R equals K times NO2 to the X, COY to the Y. The second reaction would have a rate equal to K times NO to the X, H2 to the Y. In the mechanisms that were shown, the first reaction had a two-step mechanism, where a slow step had two NO2s reacting to give NO and NO3, and a fast step where the unstable NO3 reacted with carbon monoxide to give you NO2 plus CO. It can be seen that the NO2 shows up twice in the slow step. Therefore, the order is second with respect to NO2. However, the other reactant, carbon monoxide, only shows up in the fast step. Therefore, the reaction is zero order. So the experimental rate is second order with NO2, zero order with CO, explaining why you still need the carbon monoxide. However, it's not in the rate law because the reaction is already essentially controlled by the rate determining step by the time the carbon monoxide shows up. The second reaction had a three-step mechanism. A fast step where NO and NO made an intermediate N2O2, a slow step where the intermediate reacted with hydrogen to give you water and N2O, and another fast step where the unstable N2O gave you hydrogen, nitrogen, and another water. In this case, NO, you have two steps before the at or before the slow step. The NO shows up twice, so the order is second. Hydrogen shows up twice also. However, it only shows up once before at or before the slow step and once after, so the order is only first order. Generally speaking, reaction orders are either 0, 1, or 2. However, times do show up where you get reactions that are either fractional or in the denominator. We will look at both of those and why they occur, because again, the order does give you an insight into how the reaction occurs. How non-integer reaction orders occur can be seen by examining two reactions. The equilibrium between bromine and two bromine radicals, and the equilibrium between a bromine radical and hydrogen to form HBr and a hydrogen radical. Individually, these are two separate equilibrium reactions. However, if one combines them, one gets a chain reaction. Combines them by taking the forward reaction of one, bromine going to give you two bromine radicals, with the forward reaction of two, the bromine radical reacting with hydrogen to give you a hydrogen radical. When these are combined, you get a third reaction. The Br2 will react with the hydrogen to give you hydrogen bromide and bromine. At this point, you will note that the bromine radical, that is the product of reaction 3, is the reactant of reaction 2, and the hydrogen radical, that's the product of reaction 2, is the reactant in reaction 3. You have now what is called chain propagation. The product of one reaction becomes the reactant for the next. The formation of the initial radical is called the initiation step. However, you now take the reverse reaction where the hydrogen radical and the HBr give you a Br reaction and an H2 from reaction 2. You have a bromine radical and a bromine radical now present, and you get a fifth step where the two bromine radicals recombine to give you the reverse of reaction 1 in what is known as a termination step. The overall rate of the reaction is the rate to make the product. The rate to make HBr is going to be the rate of reaction 2 plus the rate of reaction 3, where HBr is made, minus the rate of reaction 4, where it is lost. If I look at this in more detail, that's going to be K2 times the bromine radical times hydrogen, plus K3 times the hydrogen radical times bromine, minus K4 times the hydrogen radical and HBr. You will notice that you have two reactive intermediates here that have to be replaced. The bromine radical, which is found in the first reaction, where the forward and reverse reactions are equal in equilibrium. So K1 times Br2 is K minus 1 in reverse of the bromine radical squared. So the bromine radical can be replaced by K1 over K minus 1 times Br2 to the 1/2 power. You notice now that you have a non-integer power, a non-integer order. Fractional orders are usually indicative of reactions involving radicals. To replace the hydrogen radical, you have R2 is equal to R3 plus R4, which can be expanded as shown, as the hydrogen radical is made in R2 and used in reaction 3 and reaction 4. So you get a complicated equation where, once again, you have a fractional exponent for the order for the bromine. So overall, the hydrogen radical is shown as such, which is admittedly complicated. You have two fractional orders present. So, I have my initial premise that the rate of producing hydrogen bromide is the rate of reaction 2 plus the rate of reaction 3 minus the rate of reaction 4. The rate of making the hydrogen radical can be set equal to 0. This is called a steady state approximation. Essentially, once a radical is produced, it is also used. So at any given time, the concentration of a radical in a reaction is going to be 0, and this can be used to subtract these two equations to simplify that the rate of making hydrogen bromide is simply 2 times K3, since that is present in both reactions, times the concentration of the hydrogen radical times Br2. Substituting for the hydrogen radical, you get, again, a long, complicated reaction, which now has another aspect to it. Not only do you have a fractional order in the numerator, you now have reactants in the denominator. Simplifying this to some degree, you still have, again, numerator and denominator. And now you have two separate rate constants, a K going forward and a K going backwards. So, for chain reactions or for non-integer reactions, you have clues in the order of the reaction. If you wind up with a fractional order, 1/2, 1/3, 1/8, that means there is a radical someplace involved in the reaction. Remembering once again that these orders are experimentally determined. Experimentally, if you determine that you have a negative order, in other words, you have something in the denominator, something to the -1 or -2, that is an indication that you are also looking at, if you get that experimentally, it means you are looking at a chain reaction. Second special case in reaction kinetics is catalysis. A catalyst can be any surface of any material. The key point is that it has to be highly porous and have a high surface area. Surfaces in general are reactive because they're only partially coordinated. Half of the molecules are in the material and half are outside. Because of this, they are highly reactive. In catalysis, what occurs is a molecule will be attracted to this reactive surface. This is the same reason why furniture gets dusty if you don't dust it. It's a flat surface. It will attract anything to complete the coordination. Once the molecule is attached to the surface, it is basically pulling in two directions. So the bonds become weaker, lowering the reaction energy. With the net result is that it's now easier for a new bond to form since the activation energy has been lowered, and you get a product molecule floating away. That is the basis of all catalysis. Special interest is enzyme catalysis. An enzyme is any biological molecule that generally has chiral centers so that it is able to attach some molecules and not others, and it's very specific in this. Substrate is whatever molecule is going to be attached to the enzyme. So the substrate can do one of two things. Once it attaches to the enzyme, it can either detach once again, in which case you have an equilibrium step where the enzyme and the substrate simply exist in equilibrium with some sort of enzyme substrate adduct. Or conversely, once stuck to the surface of the enzyme, activation energy could be lowered and it could form some product. Putting these two cases together, it's obvious that the rate, if you're interested in making product, is equal to the constant of the second step times the concentration of that enzyme substrate combination. Using a steady state approximation, you're making the enzyme substrate and losing it in step 1, and you're also losing it in step 2. So, I look at the enzyme. The concentration of free enzyme from the steady state approximation is K1 plus K2 times the combination divided by K1 times the substrate. Total enzyme, however, that was present, is the free enzyme plus whatever's bound to the substrate. So, combining these, the enzyme substrate combination is equal to some constant times the total enzyme concentration times the substrate divided by 3 constants times the concentration of substrate. This can be simplified slightly by dividing everything by K1. Why you do this is that you wind up with a simplified way of saying something. K2 times the original total concentration of enzyme is some constant V. The sum of all the products in the denominator is some constant Km, which is the Michaelis-Menten constant. So enzyme catalysis is a 2-step mechanism where the first step is an equilibrium step. This leads to a compound rate law where things are simplified by reducing it to 2 constants, one V, the meaning of which will be seen in a second, and the Michaelis-Menten constant, K sub m. You have 2 possible limits in this case. In the first limit, what happens if the concentration of the enzyme substrate is much larger than the value of K sub m? In this case, the denominator simply becomes the enzyme substrate concentration, which then cancels, and the rate is equivalent to that constant V, or K2 times the total concentration of substrate. This is called the limiting rate, because in this case, rate 2 is the rate determining step. The amount of product you make is determined by how much enzyme substrate concentration that you get. However, in the second limit, if the concentration of substrate is much smaller rather than the Michaelis-Menten constant, you get the rate is equal to the rate limiting step times substrate over the Michaelis-Menten constant. Essentially, you wind up with a situation with a lot of various different rate constants thrown in. The net result of that is that step 2 is the rate limiting step. There is an excess of enzyme substrate adduct formed, so the limitation is the activation energy to form the product. Key point here is that if you have a catalyzed reaction in general, especially an enzyme catalyzed reaction, there really is no rate determining step. This is actually unique in chemical reactions. So it has been shown that the order of a reactant determined experimentally is an indication of how that reaction occurs, the mechanism. In general, the order tells you how many times an individual reactant occurs at or before the rate determining step. If one winds up experimentally with a fractional order, that means you are looking at a reaction that involves a radical. If you have experimentally determined a reaction with a negative order, with an order in the denominator, that tells you have a chain reaction. And especially catalyzed reactions are shown to be more complicated because they do not have a rate determining step. In future videos, linked in the description below, we will examine the impact of temperature on the rate of a reaction. Thank you, and I hope you found this video useful.